Good day. I'm Arvin Enriquez, your subject teacher for probability and statistics. With this video lesson, we're going to discuss the topic hypothesis testing and identifying the parameter of a real-life problem under your probability and statistics. Our lesson objectives. At the end of this lesson, you are expected to illustrate the null hypothesis, alternative hypothesis, level of significance, rejection region, and types of errors in hypothesis testing. Second, identifies the parameter to be tested given a real-life problem. So for the introduction, we make decisions every day. Yes, definitely we make decisions every day. Some of these are important while others are not because some decisions that we made are somehow a life changing. In decision making, we usually follow certain processes. Weigh alternatives. So what are the possible alternatives? No? So once we decide for this one, what are the possible alternatives or the better, no? The much better decisions that we can arrive on the same result. Collect evidence. If I'm going to decide for this, no? So we need to collect evidence that will serve as our basis in our decision. And right after collecting evidence, we need to make our decision because we already have your evidences, no, as our basis in making or I mean in making our decision. After a decision is made, an appropriate interpretation is made, or an action is undertaken, we follow the basic processes in testing hypotheses in statistics. Here in your testing hypothesis in statistics, so there is an involvement of test statistics. So it can be your C test, your T test, your P test, and other test statistics for us to verify, no, if these hypotheses or these assumptions or claims that we made, no, at the beginning of our research, no, is acceptable or not. So by the means of this testing hypothesis, no, or with the use of test statistics, we can verify if the claims are true or not, or the claims are acceptable or not. So that's how we process, no, before we conclude that this statement is acceptable or not, useful or not. Every hypothesis testing begins with the statement of hypothesis. Should, we should begin with the statement of hypothesis because if there is no statement of hypothesis, then what is the sense of going forward with your hypothesis testing? A statistical hypothesis is an inference about a population parameter. So in a research, no, dealing with your population, dealing with the sample, we always look for a parameter to be compared to your computed value, or I mean your population mean. So this inference may or may not be true. Anyone who watch commercial TV, for example, cannot fail to be aware of the constant varieties, no, new 5 of claims, brand X detergent will wash while clothes sparkling white. With a certain gasoline, your car will get more kilometers to the liters than before, and so on and so on. So these are the possible claims, no? I mean, these are examples of claims, no? Or hypotheses or assumptions that some people or peoples made, no? So the only sure way of finding the truth or falsity of a hypothesis is by examining the entire population. In some cases, subjecting your a sample from your population is not enough for us to see that our claims are acceptable or not. That's why uh, at some point, most of the researchers know they subject the entire population. And to make this conclusion more reliable, more valid, and more acceptable to adapt, no, of other people. Because dealing with research, that's why in dealing with your research, no, or I mean, dealing with research, we are more on solving problems. We're looking for possible interventions um, that we can deal with to make this life more easier to deal with, or by giving recommendations for future researches. Because this is always not feasible, a sample is instead examined for the purpose of drawing conclusion. Again, no, there are times that we need to subject the entire population, but most of the time, we only get sample from that population to represent the entire population. But dealing with this sample, there is always an error because you cannot say that if we subject the 30 persons, no, out of 100 persons, it doesn't mean that 30% will represent the entire 100 persons. But in research, we only subject the sample, no, for the purpose of drawing conclusions. But if you want a more reliable, a more valid conclusions, you need to subject your entire population. But again, it is not always feasible. That's why we are just dealing with a sample from that population to represent the entire population. And for us to conclude based on the sample that we subjected now in your research. For the definition of terms, so the following terms are frequently used in hypothesis testing. So first, let's start with your null hypothesis. So it's denoted by HO. So we simply use HO to represent your null hypothesis. In a statement that there is no difference between a parameter and a specific value, or that there is no difference between two parameters. So your null hypothesis always show equality, no, between your parameter and your specific value. So for example, if we use a variable y to represent your, for example, your specific value, and we use variable c to represent your parameter, then y is equal to c. If we're going to state your null hypothesis, we can simply use a symbol that y is equal to c, meaning say that there is no significant difference between your parameter and a specific value. So as a researcher, we don't want this type of hypothesis. Why? Because as a researcher, we always want to prove, no, that there is an existing uh, differences, no, between your parameter and your specific value. Because it's nonsense dealing with a research, no, that we accept the claims that the parameter is equal to your specific value. So again, as a researcher, we always want to prove that there is an existing uh, difference, no, between your parameter and specific value. Second term, so your alternative hypothesis. So we simply use age A or age sub A to represent your alternative hypothesis. So it's a statement that there is a difference between a parameter and a specific value, or that there is a difference between two parameters. So somehow, alternative hypothesis is a totally the opposite of your null hypothesis. No. So for example, as long that your statement or your claims, no, that does not show a an equality, I mean, no, between your parameter and a specific value, so that will be your alternative hypothesis. So it can be less than, greater than, or not equal to. As long that your parameter is not equal to your specific value, or our statement, no, pertains that our parameter is not equal to your specific value, then your type of hypothesis is an alternative hypothesis. For the third term, which is your level of significance, is a predetermined error which the researcher is willing to risk in rejecting the null hypothesis when it is true. So this level of significance, this will be your alpha. When we say, or when we are dealing with your alpha, no, as a researcher, this will be the maximum error that we want to encounter, or we want to meet in your research. So what are the common values for this level of significance? First is your 0.01, 0.05, and 0.10 that we can map on the confidence interval values, which are 90, 95, and 99. Because if we're going to add this level of significance, no, to your confidence interval, so that will be equal to 1 or 100%. For the fourth term, which is the rejection region or the critical region, is the range of values of the test value that indicates that there is a significant difference and that the null hypothesis should be rejected. So for example, we have your critical value. No? Your critical value will serve as a boundary, no, between your non-critical region and critical region. Now, if the computed value, for example, your computed C, your computed T value, if this computed value, no, will fall under the critical region, you're going to reject your null hypothesis and you're going to accept your alternative hypothesis. Meaning to say, once we accept your alternative hypothesis, then we accept or we adopt the statement that there is a significant difference, no, between your parameter and your specific value. So that will be your rejection region. If the computed value will fall on this region, then you're going to reject your null hypothesis. Then for the fifth term, no, acceptance region. So is the range of values of the test value that indicates that there is no significance difference, no, and that the null hypothesis should be accepted. So there are times, no, in your research that your computed value will fall on the acceptance region or the non-critical region. Why? Because your computed value is somehow, or there is an error, no, if we commit on this type, no, that your computed value, for example, your C, your T, no, will fall on this region, then you're going to accept your null hypothesis. And we're going to accept the statement that there is no significance difference, no, between your parameter and your specific value. So that will be your acceptance region. Now, for the sixth term, the type 1 error. If the null hypothesis is true and accepted, or if it is a false and rejected, thus the decision is correct. Now, if the null hypothesis is true and rejected, so that will be a type 1 error. So once from our test statistics, no, right after dealing or right after applying your test statistics, and we from our computation, then your computed value will fall on the acceptance region, and meaning to say that we're going to accept your null hypothesis and your null hypothesis is true. Once we reject a true null hypothesis, that will be a type 1 error. For the seventh term, this will be your type 2 error. So if the null hypothesis is false and you accept it, the decision is incorrect. Therefore, if a null, even if you know that the null hypothesis is a false statement, once you accept it, that will be a type 2 error. You accepted a false null hypothesis. Now, in your eighth term, one-tailed test. So in every problem, there is a keyword. No, for example, in a problem, there is being mentioned that blah 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 is your population is less than or greater than. Then, meaning to say that the given problem needs to be tested using a one-tailed test because there is a given condition which is less than or greater than. So this one-tailed test indicates that the null hypothesis should be rejected when the test values is in the critical region on one side of the parameter. So if the problem mentioned that blah 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 your population is less than, then we're going to subject the negative part of your normal curve or the left side of your normal curve. If the problem mentioned that the population mean, or for example, is greater than blah blah blah, then we subject the right side of your normal curve. So for this one tail test, it can be left side of the normal curve or the right side of the normal curve. It depends on the keyword that you can see, no, or you will see on the given problem. Now, if that is the case, now how about your two-tailed test? In your two-tailed test, for example, if there is no words or keywords being mentioned on your problem, for example, less than, greater than, we always assume that the problem needs a two-tailed test. If there is no keyword like less than, more than, greater than, no, meaning say we're going to use your two-tailed test and we apply to your alternative hypothesis the not equal to, because we don't know if the population mean is less than or greater than from our assumptions or from the hypothesis. So your two-tailed test is a test with two rejection regions. Why? Because we both your right and left sides of your normal curve are subjected in your test, in your hypothesis testing. So in this test, the null hypothesis should be rejected when the test values is in neither of the two critical regions. If your test value will fall either of the two critical regions, then you're going to reject your null hypothesis. Now, if the case is that your test value or your computed test value will fall on in between your critical region, that will be your non-critical region. Then you're going to accept your null hypothesis. For the 10th term, the parameter is a numerical value that states something about the entire population being studied. For example, we may want to know the mean wingspan of the American bald eagle. This is parameter because it is describing all the population. Now, in testing hypothesis, we always want to check if the computed or your population mean will fall within the parameter or your population mean is equal to your parameter. So most of the time, our assumption or hypothesis will depend on that because we always assume that your parameter or your population mean will fall within your parameter or your population mean will be equal to your parameter. So that will be your parameter. So our null and alternative hypothesis. So the null hypothesis symbolized as HO always states that there is no difference between a parameter and specific value. And for the alternative hypothesis symbolized as HA states that a specific difference between a parameter and a specific value. So to state the hypothesis correctly, the researcher must translate correctly the claim into mathematical symbols. So we just simply converting a statement to a mathematical symbols for us to make things more easier to deal with. No. So there are three possible sets of statistical hypotheses. So the first one is a two-tailed test. So these two-tailed tests will be dependent on the symbols from your uh, alternative hypothesis because you don't know if that parameter is less than or greater than to your specific value. So if there is no keyword being mentioned in your problem, which is less than, greater than, more than, then we should assume that the parameter is not equal to specific value. Why? Because your alternative hypothesis shows that there is a significant difference. But if there is no keyword being mentioned in your problem, then we assume that your parameter is not equal to a specific value. As long that there is no equality between your parameter and specific value, then we can represent your alternative hypothesis. Now, your two-tailed test or your test will be dependent on the symbols of in your alternative hypothesis. That's why it's two-tailed because not equal to. We don't know if that is less than or greater than. Now, for number 2, your HO now is a parameter is equal to a specific value. So this part is not equal, no? You need to recheck this one. So this will be a colon, not equal. Your HO colon, HA colon to a parameter, which is equal to your specific value. So for number 2, HO colon, so you need to recheck that one. HO colon parameter is equal to specific value. Again, in your null hypothesis, we always assume or we always show that there is, or I mean, there is no significant difference, no? And we always show an equality between your parameter and specific value. Now, again, this left tail test will be dependent on the symbol on your alternative hypothesis. If this is less than, no, then it is left tail test. So if there is a keyword being mentioned on your problem that is less than, for example, then we apply your left tail test. As long that a parameter, no, shows that the value of the parameter, I mean, is somehow less than your specific value, and that will be your assumption in your alternative hypothesis, because your alternative hypothesis uh, will not show equality between your parameter and your specific value. Then for the third one, no, same pa rin, same with your HO colon parameter is equal to your specific value. As you can see, no, your null hypothesis in the three conditions are the same because your null hypothesis shows equality between your parameter and your specific value. For number 3, in your HA colon, parameter is greater than specific value once the keyword was being visible, no, in the problem or being mentioned on the problem that is something that parameter is greater than blah blah blah, then we need to use the right tail test. Again, whether two tail test or one tail test, it can be left tail or right tail test. It is always dependent, no, on the symbols that we are using, no, in your alternative hypothesis. So if the problem is a two tail, left tail test, and right tail test, there's always a reason why it is two tailed, why it is left tail or right tail. We cannot use left tail test if the parameter is not equal to specific value. For example, if there is no keyword being mentioned, you cannot use left tail test and right tail test because we don't know if the parameter will fall, or I mean your specific value will fall before or after your parameter. That's why we are using, for us to be safe, no? And for us to be safe in making our conclusion and to make this more acceptable and valid, we simply use your two-tailed test. So for example, number 1, so bottled fruit juice content. The owner of the factory that sells a particular bottled fruit juice claims that the average capacity of a bottle of their product is 250 ml. As you can see in the first problem, so there is no keyword being mentioned that there is a less than or a greater than portion of this problem. So answer, in the example, the owner's statement called claim is a general statement. Yes, it is a general statement. So the claim is that the capacity of all their bottled product is 200 ml per bottle. A consumer group may generalize that the bottled product is a short of the claim. If this can be proven, then the factory owner is lying. Yes, it is, no? The evidence must be established. So, the consumer groups gets interested to know if, in reality, each bottle contains 200 ml. Thus, the two hypotheses would be, first thing to do, no? In your, again, in your null hypothesis, it shows equality. So meaning to say, our claims is that the bottled water drinks contain 250 ml per bottle. So we assume that the capacity of the bottled water, no, is 200. I mean the capacity of the bottle, no, is 250 ml. So that will be your null hypothesis. Now, your alternative hypothesis, that is totally opposite of your null hypothesis. Again, a while ago, I said that there is no keyword or keywords being mentioned in your problem. For example, less than or greater than. So we simply assume, no, or we just simply state that the bottled drinks do not contain 250 ml per bottle. This is the opposite of the claims. So it shows, so your alternative hypothesis, no, does not show equality. That our claims is totally opposite of your null hypothesis. Now, how can we convert this to a statement to a symbol? Now, we simply use your mu for your average, your HO colon, your population mean, or I mean your mu, which is your mean, is equal to 250 because we assume that the drinks contain 250 ml. Now, for your HA, why is that we use your not equal to here? Because again, no, in the problem, there is no keyword being mentioned which is less than or greater than. That's why we don't know if that is a left tail test or the right tail test. That's why we're using two tail test because there is no keyword being mentioned in your problem. That's why we use the symbol not equal to because your alternative hypothesis will not show, no, I mean equality, and we assume that your mean is not equal to 250. So for example number 2, working students. A university claims that working students earn an average of 20 pesos per hour. So as you can see in this problem, so there is no keyword or words being mentioned like less than or greater than. That's why we assume that this problem needs, no, a two-tailed test. That's why your alternative hypothesis is not equal to 20. So we assume that your mean is not equal to 20. Now let's deal first with your statement. So the working students earn an average of 20 pesos per hours. So we just clean because your null shows equality, no, between your average and the given value of this 20 pesos. So the claims that the average is 20 pesos per hour. Now for your alternative hypothesis that is totally opposite of your null hypothesis, your alternative will show or will not show, I mean, equality between your average and the given values. Now, the working students does not earn an average of 20 pesos per hour. So we assume that do not earn, no? The student do not earn an average of 20 pesos per hour. So this will be the claims totally opposite of your null hypothesis. Now, once we convert these two statement to is mathematical symbol, your HO colon, your mu or your average is 20 is equal to 20 because that will be your null, your HO. Then for your alternative hypothesis, which is your HA, that is totally opposite of your HO, that will not show a equality between your parameter and your specific value, then since there is no being mentioned, no words that is being mentioned on your problem, which is less than or greater than, then we use the not equal to symbol because we don't know if that is less than or equal or greater than in reality. No, your mu or your mean now is not equal to 20. So there's always a reason why we use this not equal to, no, instead of using your not less than or greater than. Again, if there is no keyword being mentioned in your problem, then let's deal with your not equal to, because in reality, we don't know if that is less than or greater than to the specific value. Let's deal now with your hypothesis testing. In a decision-making process, no, for evaluating claims about a population based on the characteristics of a sample purportedly coming from that population. Because in research now, we only subject sample from your population. And we only subject this sample. And this will serve uh, as our basis in having our conclusions at the last part of our research. So the decision is whether the characteristic is acceptable or not. So at first, there are claims, there are assumptions based on the given situations. But as a researcher, uh, we are not just easily accept those assumptions or claims, no, based on the given scenarios or situations, no. We just really need to test the validity, the if that statement is reliable, no, if that statement is acceptable uh, to be used, to be accepted, no, then we need to deal with your hypothesis testing. This will be the process, no, in assessing and testing our claims and assumptions before we conclude that this assumption is acceptable or not. These assumptions or claims are useful or not. So by the means of hypothesis testing, we can check and assess if these hypotheses, assumptions, or claims no, are acceptable or not. So in hypothesis testing, there are four possible outcomes as shown in the table below. The null hypothesis may or may not be true, but there are times that your null hypothesis may be true. The decision to reject or not to reject is based on the data obtained from the sample of the population. So once we compare your once your computed value, your T or your C, or even if your P value no falls on the non-critical region, then you're going to accept your null. If those value falls on the critical region, then you're going to reject your null hypothesis. Now in this table, you will see a type 1 and type 2 error and a correct decision. Now for us to visualize more, now what is a type 1 and type 2 error? Now, in your HO is true, meaning to say that your null hypothesis is true. Once you reject a true null hypothesis, then that's a type 1 error. Because the correct decision for this is to accept your null hypothesis because your null is a true statement. Then, if your null is a false statement, your correct decision is to reject it. But if you accept this kind of claims or hypothesis now, even if you know that your null is a false statement, then you accept it, that's a type 2 error. Now, a type 1 error occurs if one rejects the null hypothesis when it is true. Yes, no? Once you reject a true null hypothesis, that will be your type 1 error. Once you accept a false null hypothesis, so that will be your type 2 error. So the level of significance. So the level of significance is the maximum probability of committing a type 1 error. So that will be your alpha. So when you say level of significance, that will be your alpha here. So this probability is symbolized by alpha, Greek letter alpha. So that is your P, or the probability in committing a type 1 error. So that will be your alpha. That's why I said a while ago that your alpha is the maximum error that a researcher wants to meet, because that will be a probability, no, or we can associate this alpha to a probability of in committing a type 1 error. So the probability of a type 2 error is symbolized by your beta, no, that is your P, or the probability in committing your type 2 error is your beta. Although in most hypothesis testing situations, B cannot be computed. Why? Because we simply use your alpha as your level of significance. So most of the time, or we only use alpha, or the level of significance, for our research. After a significance level is chosen, no, a critical value is selected from the table. That's why we are using your C table, your T table. It will be dependent on what type of research are we dealing with, no, if that is for or if that research needs a C test or T test, your P test, no, and other test is statistics. It will be dependent on the needs, no, being given on the problem. So for the appropriate test, so the critical value determines the critical and the non-critical regions. Why? Because this critical value, or values, will serve as a boundary, or border, no, in between your non-critical region and your critical region. It will serve as a boundary or border that will separate your non-critical region to your critical region. That will be your critical value. That's why you always compare, no, your critical value and your computed value. Because if your computed value will fall on the critical region, then you're going to reject your null. If your computed value, your C or T or your P value, will fall on something like that, no, will fall on the non-critical region, then you're going to accept your null hypothesis. So the critical region, or the rejection region, is the range values of the test value that indicates that there is a significant difference. That's why, no, a while ago I said that if your computed value will fall on the non-critical region, then you need to accept your null hypothesis. No. Then the non-critical region, or the non-rejection region, is the range values of the test value that indicates the differences. No. Again, if your value falls on the non-critical region, then you need to accept your null. If your value falls on the in the critical region, then you're going to reject your null. That's how simply dealing with this type of no, dealing with your non-critical region and your critical region. This was probably due to the chance and that the null hypothesis should not be rejected, because if your computed value will fall on the non-critical region, you should accept, no, your null hypothesis. So in decisions that we make, we form conclusions. Yes, it is, no. So in making a decision, we form conclusions, and these conclusions are bases of our actions. That's why we conduct a research, now for us to have conclusions, and what are the possible actions right after this research. So, but this is not always the case in statistics, because we make decisions based on the sample informations, because we only subject sample from a population to our research. The best that we can do is to control the probability with which an error occurs, because there are two types of errors, right? Your type 1 error and your type 2 error. What we can do is to control, no, the amount or the percentage of error, no, that can occur. So for this table number 2, the following table shows the probability with which decisions occur. Error in decision, reject a true null, that will be your type 1 error. Accept a false null, that will be your type 2 error. So the probability that we can map, no, on this type 1 error is alpha. The probability that we can map on this type 2 error is beta. Now for the correct decision, we should accept a true null because that is a true statement. And we should reject a false null because that's a false statement. Now, this type of correct decision is type A, and this for type B, your second statement. So what will be your probability now that we can map on this correct decision number 1? So for correct decision number 1, your probability is 1 minus 1. Now, if that is a correct decision, we just simply subtract this probability in committing a type 1 error to 1 because 1 represents a 100%, meaning to say there is no error. No. Once we subtract 1 or the probability in committing a type 1 error alpha to 1, that will be the probability that we can map on the correct decision. First correct decision that we can make. No? Then for the correct decision number 2, which is 1 minus beta, since beta is the probability in committing type 2 error. So once we subtract this beta to 1, that will represent a 100%. No? Meaning to say, we are just erasing the probability in committing an error. Now, if we subtract this beta to your 1 or 100%, so that will be the probability that we can map on the second correct decision that we can make. No? So for example number 3, for each of the given, do the following. So first, draw the normal curve. Second, locate the C-value. And third, indicate the C-value in the rejection region or in the acceptance region. Now, for number 1, your C is equal to 2. Then, with a 95% confidence interval, so meaning to say that your alpha is equal to 0.05. So in this case, your C critical values is equal to 1.96. That's why if you try to look at this one, this border now between your non-critical and critical regions, that will be equal to your critical value, which is equal to positive and negative 1.96 if your confidence interval is 95% and your level of significance is 5%. So that will be a two-tailed test. Now, if we're going to put this C, which is equal to positive 2 here, that will be inside your critical region. That's why you're going to reject your null hypothesis. Same thing with this one. If this is 95% for number 2 and it's a two-tailed test and it's automatic that your alpha is 0.05, then your C is negative 2.68. It will fall somewhere here, no? Negative 2.68 is uh, less than, no? Negative 1.96 because this value of critical regions is it's two-tailed test, no? It is positive and negative. Negative for the left side and positive for the right side of the normal curve. Now, since negative 2.68 is less than negative 1.96, then it will fall on the critical region, meaning to say you need to reject your null hypothesis. So for examples of testing hypotheses using C-tests, a manufacturer claims that the average lifetime of his light bulbs is 3 years or 36 months. So once we convert this 3 years to months, that will be your 36 months. The standard deviation is 8 months. 50 bulbs are selected. So we only subject 50 bulbs for this research. 8 and the average lifetime is found to be 32 months. Should the manufacturer's statement be rejected at level of significance which is equal to zero point 0.1? So our solution now, we need to state first your hypothesis. Now, in your null hypothesis now, we assume that your mean is equal to 36 months because we are dealing with your 3 years or 36 months. Then for your alternative hypothesis, no, that will be your mean is not equal to 36 months because there is no keyword or words being mentioned in your problem that is less than or greater than. That's why we assume that your mu is not equal to 36 because we don't know if that is less than or greater than in reality because there is no word or keywords being mentioned in your problem. So for step number 2, we need to identify the test statistics to use. So we're going to use your C-test. So with a given level of significance with zero point 0.1 and the distribution of the test statistics, state the decision rule and specify the rejection region. So we're going to use this formula in finding your computed C value that we're going to compare for your critical value using your value using your level of significance which is equal to zero point 0.1. The symbol not equal to in the alternative hypothesis indicates that the test is in total test. A while ago, I said that if you're going to decide if that is a two-tailed or one-tailed test, it will be dependent on the symbol that we use on your alternative hypothesis. So with two rejections region, definitely because that is a two-tailed test. So one in each tail of the normal distribution curve of your sample mean. So because the total area of both rejection regions is zero point 0.1 or the level of significance, no, the area of the rejection region in each tail is, so we just simply compute in this scenario. So that will be alpha over 2 or equal to 0.1 over 2 is equal to 0.05. So in the C table, using your C table, the C value that we can map on 0.05 is equal to 1.645. So we just simply look for the value that we can map on this value. Why we divide this alpha by 2? Because your test is a two-tail test. That's why we need to divide your level of significance by 2, equally divided, alpha over 2 to the left side and alpha over 2 to the right side of your normal curve. So we apply this 1.645 as the value of your C value that we can map on your 0.05 as the value of your alpha over 2 in each side of the normal curve. So as you can see in this figure, we apply now the value of your alpha over 2, which is 0.05. So this will be your alpha over 2 here and alpha over 2 here. Now, if your C is negative 1.645 and positive 1.645, no? Because we apply the positive and negative sign of your C value from your C table because it's a two-tailed test. No, your negative C sub alpha over 2, no, our decision rule. So we need to reject the null hypothesis if the C is greater than C sub alpha over 2 is equal to 1.645, or your C now is less than negative C sub alpha over 2, which is equal to negative 1.645. So we need to satisfy this condition before we reject your null hypothesis. So for step number 3, we're going to compute the value of the test statistics. So we're going to use this formula for your C, and for us to compute for the value of C. And now we just simply substitute the given value, which is your 32 or your sample mean, 36 that is your population mean, and your 8 is your population standard deviation, and your 50, because we only subject 50 in your research, that will be your sample size now, or equal to n. So by simply by simplifying these given values with operations, we arrive with negative 3.54 as a value of your computed statistics in C, or the computed value for C. Now, in step number 4, state the decision rule. So we're going to reject your null hypothesis. Why? Because negative 3.54 on your step number 5, no? Why we need to reject your null hypothesis? Because we are just comparing this negative 3.54 and your negative 1.645 here. Since negative 3.54 is less than in your critical region is critical value, which is negative 1.645, then it will fall on the rejection region in the left tail. So meaning to say you're going to reject your null hypothesis, no? Because your computed value for C is less than on the critical value that we got from your C table. Therefore, your HO now and the and conclude that the average lifetime of light bulbs is not equal to 36 months, because we need to reject your null hypothesis and we adopt your alternative hypothesis, meaning to say it can be less than 36 months or greater than or more than 36 months. So that will be our conclusions. We need to reject your null and we need to adopt your alternative hypothesis. So for activity number 1, so answer the following questions carefully. So between your HO, which is your null, and your HA, which is your alternative, what is a good reason for starting a hypothesis test with HO? Why is that you need to start with HO? For number 2, suppose it is the Christmas season and Janine thinks that it is the month of January. What, what error is she committing? So for number 3, what type of error is committed when you reject a null hypothesis when in fact it is true? So thanks for watching. If you want to like, comment, share, and subscribe, so please do so. So I'm Arvin Enriquez, your subject teacher for probability and statistics.